Good morning, young chemistry students. Today we're going to discuss the atom. Of course, we love the atom. I love the atom. So here we go. We start off with a little comic. I lost an electron. Are you positive? So we'll find out soon that when you lose an electron, or not you, when an atom loses an electron, it becomes a cation, which is a positive ion. First off, to start, an atom consists of a nucleus that's made up of protons and neutrons. Protons and neutrons are inside of the nucleus. What you will find, though, is you see all of this area here. It looks like there's electrons just everywhere. There are not that many electrons actually in an atom. Those electrons instead, all those dots are showing where electrons have been. Those electrons are moving so incredibly fast that it looks like there's electrons everywhere, and it's almost like a solid wall. I always laugh and think about the time when my little boy, Adam, who's not so little anymore, but he used to want to be the Flash, and he'd run up to me and he'd say, "Mom, look, I'm the Flash," and he'd go, and just rub his hand, like wave it across his face, thinking he was so fast. And that's kind of like what the electrons are doing. The electrons are moving so fast, it's almost creating like a solid wall, which is pretty crazy to think about. So an atom is honestly like, it's exciting to me, might be to you. This is called the electron cloud, where those electrons are moving about. And there's a space that's semi-assigned to these. It's not, notice though, it's not like an orbital path or anything like that. These electrons are not in a perfect little pattern. They're more so just assigned to a certain space within the atom, and they stay in that particular space because electrons repel. These electrons, they have a negative charge. So of course, when we have like charges repel instead of attract. We'll get more into that soon. The nucleus is where the density is. It's very dense inside of an atom, and that's where the mass is, and we'll find that out in just a couple slides here. I do want you to take some time, this Power of 10 video, I'm not going to show it now, but I did post it on our Schoology, and I would like for you guys to watch the Power of 10. The reason why I like this Power of 10 is because you have been studying biology, and so you're thinking cells. Your mind's on cells. Your mind's on, oh my gosh, they're so tiny. We have to look through a microscope. And I want you to imagine what the size of an atom is in comparison to everything else. Another thing I also love here, it says a cube of sugar contains as many atoms as there are stars in the universe. Obviously, we don't know for sure how many stars there are in the universe, but we can also say we don't know for sure. No one sat there and counted the number of atoms in a sugar cube. However, we have counted the number of atoms in a very small space, and we do know the mass of the atom. So we can approximate the number of atoms based on all that. The atom consists of subatomic particles, and we call the protons, neutrons, and electrons subatomic particles. That means they're part of the atom. The protons, notice they're positively charged. I do want you to notice right here the P+. This is a common way to represent protons. So you don't have to write out protons every single time you're doing an assignment or even on a lab. Like, this is a common chemistry language between other chemists. Protons are located inside the nucleus. They are the positively charged particle. We will soon find also that the protons do not change. The number of protons do not change in an atom. If the number of protons changes in an atom, the identity of the atom changes. So you're not going to have a proton fluctuation unless the identity of an atom changes, which is slim to none of that happening. A neutron is located inside the nucleus also, and that's a particle with no charge. Notice neutron, neutral, there's no charge. Again, we can write it like this little N with a superscript of a 0. That's a handy way to write neutron instead of having to write it out every time. And finally, the electron is located in the orbital surrounding the nucleus, and it is, of course, a negatively charged particle. And the method in which we write electron is E, and then a superscript of a minus charge. This right here, you don't have to know these exact numbers, like the actual mass and everything. What I want to point out to you, though, is first off, the electron, you can see the symbols and the charges again. But what I want you to see in particular right here is this number right here, the relative mass. So the mass of a proton and a neutron, let's say each of them have like what we call as a 1 atomic mass unit, or 1 AMU. We can just say, hey, there's a proton in there and there's 1 AMU. There's a neutron in there. There's 2 AMUs total for the nucleus. But look, this electron is 1/1800th the size of a proton or a neutron. So therefore, these protons and neutrons are 1,800 times the mass of an electron. The reason why this is important is because when we calculate mass number or average atomic mass of an atom, we don't calculate the electrons. The electrons, the mass of the electrons are actually negligible, so we don't even need to worry about that. So again, the mass of a proton or neutron is 1,800 times the mass of an electron. So therefore, the atom is mostly empty space. And if you were here with me, I'd take you on a little field trip. And so the field trip, what I do is I take a marble. I take a marble outside with me, and I say, okay, if this marble is the size of a nucleus of the atom, and let's say we place that marble on the center of Lauderdale Memorial Highway, and we said, hey, we had a speck of sand. We had a speck of sand that represented an electron. Where would the closest electron be in comparison to our nucleus on Lauderdale Highway? And I have students walk to see where they think that nearest electron would be. And the funny thing is once they keep walking, and students choose all sorts of areas, but you actually have to walk clear out to the stairs that lead up to the football stadium parking lot. That's how far in relationship an electron, the nearest electron to a nucleus would be, which is crazy to think about, but actually the atom is mostly made up of empty space. And so that's why I like to do that little activity, because it helps us to think about, okay, so the mass is found in the protons and the neutrons, but the volume of an atom is mostly empty space. Here's another, just, if you could think about, if the nucleus was the size of a tennis ball, there would be about a half a mile difference between the nucleus and the nearest electron. I love this little fact here, and actually this was made before the population was over like 7 billion. But if all of the empty space was removed from the atoms that make up every single human on Earth, the entire global population would fit inside of an apple. So think about, if all of the atoms that make up all the molecules that make up our body, if we took all the empty space out of those atoms, literally we could, like, all of our cells volume-wise could fit into an apple. That's insane to think about. So to count the pieces, we have to figure out how many protons, neutrons, and electrons for the atoms. And this is like the fundamental, a lot of you guys know this already, but I want to give you a reminder here. So first of all, you need to know the atomic number. You need to use that language, atomic number. The atomic number is the number of protons in an atom. You'll find the atomic number typically at the top of the periodic table of the square. The atomic number also tells us the number of protons, which determines the kind of atom it is. So for example, if I have 6 protons, I have a carbon atom, period. If I have 5 protons, I no longer have a carbon atom. I have to have 6 protons to have a carbon atom. Protons, again, they're the identification piece, and those protons do not change. Remember, the identity of the atom changes if the number of protons change. So the atomic number is also in a neutral atom. It's the number of electrons, because think about this. If you have, say, for example, 6 positively charged particles and 6 negatively charged particles, a +6 plus a -6 is equal to 0, which means no charge. So if you have a neutral atom or an atom with no charge, you're going to have the same number of protons as you do electrons, because they have to cancel one another out. The mass number, this is where students typically get messed up. The mass number is the number of protons plus the number of neutrons, because we have to consider, where does the mass come from in the atom? Remember, I told you just a couple slides ago, an electron's mass is 1/1800th the size of a proton or a neutron. So that's why we don't count electrons in a mass number. We simply take the number of protons plus the number of neutrons. The reason why we can say the actual number of protons or the number of neutrons is because each of them weigh 1 atomic mass unit, which helps us to determine sizes and amounts and so forth. So let's do a couple of practices here with some symbols. This right here is what we call an isotopic symbol. And this isotopic symbol, you'll always see the mass number is going to be written in the upper left, and the atomic number is going to be written in the bottom left of the actual symbol of the atom. Now, keep in mind, when in doubt, and you're like, oh my gosh, I cannot remember which is the mass number, which is the atomic number, the atomic number is always going to be smaller than the mass number unless you're working with something like hydrogen. So atomic number again tells us the number of protons. The mass number tells us the number of protons plus neutrons. So let's do some practice here. We have fluorine, and this is called, we refer to this as fluorine 19, because that's the mass number of this particular fluorine. So what we want to do is find the number of protons, neutrons, electrons, the atomic number, and the mass number. Looking at this right here, our atomic number is 9. So that tells us the number of protons is 9. We're going to find our mass number, and we're going to subtract our atomic number from it, because remember, the number of protons plus neutrons equals your mass number. So we have 10 neutrons. The number of electrons, notice there are no indications of an ion here. So the number of electrons, this being a neutral atom, is the same as the number of protons, which is 9. And therefore we look and we have our atomic number is 9 and our mass number is 19. Let's take a look at bromine. This is bromine 80. We call this, we refer to this in isotopic form, and we'll learn more about that soon, but we call this bromine 80. Again, find the protons, neutrons, electrons. We have protons is 35. It matches the atomic number. Neutrons, we're going to take our mass number and subtract our atomic number from it, and we get 45. The electrons, there's no indication of an ion here, so therefore we're going to get 35 again, because the protons and electrons cancel one another out. Our atomic number is 35. Our mass number is 80. Let's try this one. So we have sodium, and sodium 23, because that's our mass number. We have the number of protons matches our atomic number. The number of neutrons is the difference between the mass number, subtract the atomic number, or the mass number minus the number of protons. There's no indication of an ion, so therefore there's 11 electrons. 11 is your atomic number, 23 is your mass number. So this is just some very basic parts. I'm going to have another video about ions and isotopes, so hang in there with me. If you guys have any questions, please make sure to contact me or see me in class, or just give me a heads up and say, hey, Miss D, I need to come in for math. So hope to see you again soon.